All right, so again, I'm going to try to go over or I will go over the problems from the quiz from yesterday and show you how to solve those. And hopefully this will be helpful if you have any questions. The first question was, I believe, to compare or arrange the following from weakest attractive forces to strongest. So we had CH3Cl, we had alcohol, or ethanol specifically, CH3CH2OH, and the last one was C3H8. Yep, okay. C3H8. So in this one, I would have carbon, and it would be bonded to chlorine, and then 3 hydrogens. Here, I've got this carbon bonded to those 3 hydrogens, the next one bonded to those 2, and then we have that OH alcohol bond, and here I have a straight chain of the 3 carbons, so that's just propane, the alkane. So here, all I would have are dispersion forces. Here, I would have dispersion forces, dipole, and I have specifically that oxygen bonded to hydrogen. So I should have hydrogen bonding as well as the other 2. And here the chlorine is much more electronegative. So I would have a partial negative charge here and a partial positive charge at the bottom of this. So I would have dispersion forces and dipole. So from weakest to strongest, it should look like that. All right. Next question asked for which would have the lowest vapor pressure. So we had again, ethanol. We had O2, and we had this ether. So lowest vapor pressure means strongest intermolecular forces, because they're going to be held more tightly. A smaller fraction of them are going to have enough energy to become gases and contribute to that vapor pressure. So in this case, here all we have is dipole, or not dipole, sorry. We have only dispersion forces. Here I have dispersion forces and I have a dipole because of that electronegative oxygen. Here I have dispersion forces, I have a dipole, and I have hydrogen bonding. So this should have the strongest intermolecular forces and therefore the weakest or lowest vapor pressure. Next, I'll just read it up. Substances with weak intermolecular forces have higher vapor pressures than substances with strong intermolecular forces, and the reason being that less energy is required to overcome weak intermolecular forces compared to strong ones. And that would be accurate. So the assertion is correct. Substances with weak intermolecular forces have higher vapor pressure. They're held less strongly, so less energy needs to go into them to separate them and for them to become vapor. And that was the reason given, is that less energy is required to overcome those weak intermolecular forces. So the assertion is correct, the reason is correct, and the reason is directly related. The reason is why that assertion is correct. Determine the kinds of intermolecular forces that are present in NCl3. So we need to write out NCl3 again. So I have that nitrogen trichloride, and if we do the Lewis dot structure, if we start even with just nitrogen, nitrogen has 5 valence electrons. So we'd go 1, 2, 3, 4, and now we have to pair it up. So we have one lone pair there. And then these chlorines have 7 valence electrons. So they're going to form a bond here, just like that. So I'm going to have a single bond to each one of those chlorines. but the molecule is not trigonal planar because of that lone electron pair on the top here. It is going to push those chlorines down and give it a trigonal pyramidal shape instead. And the nitrogen, or we're going to have, actually the chlorines are slightly more electronegative. So these would have, I believe, partial negative charge at the top and the partial positive charge here. But we should have a polar molecule. So we're going to have dispersion forces, but we're also going to have dipole-dipole present here. Next question was, which of the following pairs would form homogeneous solutions? Okay. So we had, what was it? KCl and water. We had CCl4 and water. Br2 and CCl4. And lastly, methanol and pentane. Okay. All right. So this first one, you may notice potassium chloride. This is a metal, and this is a non-metal. So this is actually an ionic compound. And water is polar. It has hydrogen bonding and a dipole. So this is actually going to give us an ion dipole. So we would expect that the potassium chloride would dissolve in the H2O, and we'd get a homogeneous solution or an equally distributed solution. With the carbon tetrachloride, I have a tetrahedral molecule. So the chlorines they have all equal bond angles, and they're more electronegative than the carbon, but they're all, because they're at equal bond angles, going to be pulling with the exact same amount of pull in all opposite directions. So there's not going to be any net dipole in this one. So this would only have dispersion forces, whereas the water would have dispersion forces and dipoles and also hydrogen bonding. So this is polar and this is non-polar. So these are not mixable. So we could actually, we'll just draw an X through those. Br2, bromine's relatively electronegative, but it's just two bromines bonded to each other. So there's no greater pull from one than the other. So we would have just dispersion forces here. And we already talked about carbon tetrachloride. It also just has dispersion forces. So these are non-polar. And since they're both non-polar and like dissolves like, this and these would both form homogeneous mixtures. For the methanol, we have hydrogen bonding as well as the dipole-dipole and London dispersion forces. So this is polar. With this, we just have a straight chain of carbons with only hydrogen bonded to it. There is not a noticeable electronegativity difference between carbon and hydrogen. So this only has dispersion forces. It is non-polar. And therefore, since one is polar and the other is non-polar, we would not expect them to form a homogeneous mixture. All right, so I think, yeah, that was all those. Let's jump into one of these questions here so we can see it a little better. That's what I wanted to do. Let's go over here. If I can find the nice picture. Oh, I can. Okay, good. All right, so sorry about that. Here we go. Should be able to see this picture here, the distribution of thermal energy. So in A, we have lower temperature, and B, we have higher temperature. So same substance, two thermal energy curves, one for that substance at a lower temperature, the other at a higher. And this dashed line being the amount of kinetic energy needed to escape that attractive force or to enter into the gas phase. So one asked, what would be the area or the fraction, there's the part of this graph where these molecules would have enough energy to become gases at low temperature. So if you follow that blue curve, it would only be the area right here, D, the area under the blue curve to the right of that dashed line. And the other version of the question asked which one would be at high temperature. So since high temperature is B, in red, if we follow that curve, we can see that that would be area C, this larger area under the red curve to the right of that dashed line. So this is everything. I'm going to stop the video here, upload it. Hopefully you found this helpful. If not, shoot me an email or feel free to ask questions on Monday.